Hello everyone, this is Ritika Jain and I would like to welcome you all to my presentation. My presentation is on binary state prediction of sleep or wakefulness using EEG and EOG features. Now, sleep is not defined discretely, rather a continuum of various physiological states. And three broad classes are wakefulness, REM, that stands for rapid eye movement, and non-REM, that is non-rapid eye movement. Now, our focus in this work is to achieve a high classification accuracy for the distinction of only two states, that is sleep and wake state. In future, we would like to use this binary prediction model to determine the sleep or wake phases in coma patients. Because there is no well-defined sleep-wake cycles for these patients. Hence, an accurate model that can predict these two states in coma patients is of utmost importance to the clinicians. Now let's talk about the methodology. So in this work, we have extracted features from both EEG as well as EOG channel. The EEG features that we have derived are Higuchi fractal dimension, autoregressive model parameters, and sample entropy. And the EOG features that we have considered are spectral power and sum of absolute differences. On the left hand side, you can see there's the flow chart of the proposed algorithm. So we are providing raw data and annotations as the input. And in the pre-processing step, we are using a bandpass filter with cutoff frequency of 0.5 to 45 Hz. Then EEG signal along with the horizontal EOG signal, both are considered and the feature extraction takes place. All the three EEG features and the two EOG features and various combinations are fed to the classifier. Now, we have used these 5 classifiers, that is LDA, linear discriminant analysis, linear support vector machine, SVM with an RBF kernel, KNN, and decision tree. And finally, we have presented the best combination of features and classifier. So here we have compared the performance among these 5 classifiers and reported the best one. And the final output is nothing but the predicted result, and it is in the form of two-state hypnogram. Now, hypnogram is nothing but a plot that shows the discrete levels as the different sleep stages. Now, here are the experimental details. So, the dataset that is used is sleep EDF. Number of subjects are 8, out of which 4 are healthy and 4 with mild difficulty in falling asleep. The channels that are available in the dataset are 2 EEG, where PZOZ and FPZCZ are there, 1 EOG and 1 EMG. The channels that we have considered are 1 EEG, that is PZOZ, which we have considered in this study because it provided better performance than FPZCZ channel, and 1 EOG channel is also used. The sampling rate is 100 Hz, the total number of epochs are 15188, and the scoring criteria that is there is RNK scoring system. Now the table here shows the epoch distribution for the sleep and wake stage for each of the 8 subjects. Now we have already mentioned that we have derived 3 EEG features, and they are autoregressive model parameters, HFD, and sample entropy, where AR parameters are used to predict the current value of the signal based on the past values. HFD is basically a non-linear measure, and it can be used to estimate the dimensional complexity and self-similarity of the signal. Sample entropy provides the irregularity of the signal, and the EOG signal features are spectral power, which calculates the power in the frequency which is considered here is 0.2 to 2 Hz, and sum of absolute differences. Now let's delve into the results that we have obtained. So here you can see the topmost plot is for the hypnogram, and you can see there are two states, 0 and 1, where 0 is for wake and 1 is for sleep state. Then next is the AR model first coefficient. So we have used 8th order AR modeling, but here I am showing you only the first coefficient plot. The next one is the sample entropy plot, and the third one is Higuchi fractal dimension plot. So we can see that all the 3 plots show similar behavior, in which the wake state is showing a higher value as compared to that in the sleep state, which shows that in the awake brain, the dimensionality as well as the entropy is much higher. The next plot on the right hand side is a box plot that shows 25th, 50th, that is median, and 75th percentile of the EEG features, that is sample entropy, first AR coefficient, and HFD during the wake and sleep states. So red one is for wake and blue is for the sleep. And we can clearly notice that the first AR coefficient is providing the best classification between these two states. And hence it is the best feature. Now here is the epoch-wise EOG feature shown. The first one is hypnogram for the same subject as it was in previous slide. The second is the sum of absolute difference or SAD. And the third one is the spectral power of the EOG signal. And we can see again it is much higher in the awake state as compared to that in the sleeping state. Now here is the predicted hypnogram as well as the actual hypnogram for two subjects. On the left hand side it is for subject number 1, which is a healthy subject, and on the right side it is for subject number 8, which is a subject with mild difficulty in falling asleep. So we can notice that the predicted hypnogram by our algorithm and the actual hypnogram matches a lot. So there is a lot of similarity in these two hypnograms, especially for a healthy subject, which shows that our algorithm is doing well enough. Now here we have tabulated the performance of all the features with respect to the different classifiers that we have considered. And I have highlighted the performance which is maximum. So here we can see that SVM-RBF kernel is providing the maximum classification accuracy corresponding to all the three EEG features combined together. So we can say that if we consider only a single feature, the best feature is AR. As we can see, it is providing 96.89% when we consider SVM-RBF kernel. And then finally, all the three EEG features combined together provides the highest classification accuracy of around 97.5%. The below table shows the classification performance for the EOG features only, again for all the 5 classifiers. Here also we can notice that SVM-RBF is providing the maximum classification accuracy corresponding to both the EOG features combined together. So 95% of accuracy is getting with respect to the only EOG features used. Now here we are showing the classification performance, that is overall accuracy in percentage, using combinations of both EOG and EEG features, and the best classifier is SVM-RBF. So this table is only for the SVM-RBF classifier. Now here we have highlighted the best classification accuracy corresponding to a single feature used for both the channels and when the combination of the features are used for both channels. So we can notice that the 97.5% of accuracy is achieved by using only one feature from each channel. While when we combine all the features from EEG and EOG, we are able to achieve a very high accuracy of about 98.1%. Below, we have shown a confusion matrix between the expert score and the score that has been predicted by the proposed algorithm for the wake and sleep states. On the diagonal, we can see the number of epochs which are correctly classified are 7,948 for the wake state and 6,975 for the sleep state. And we are able to achieve 98.7% of sensitivity for wake and 97.8% of sensitivity for the sleep state, which is remarkable. Now, by this, I have come to the conclusion of my presentation, and here are the points I would like to highlight. So first of all, SVM-RBF kernel provides the maximum classification accuracy for both EEG and EOG derived features. Then if we consider EEG features, AR coefficient is the one providing maximum classification accuracy, followed by HFD and SE. And if we include a non-linear feature like HFD and sample entropy, accuracy improves. So by careful choice of features, we are able to achieve a high sensitivity of about 98% and around 97.8% for the wake and sleep state respectively, which is way higher than the previously reported studies. And just by using EOG channel, we could achieve an accuracy of about 95.2%, which makes it very suitable to use in the situations where EEG can't be used. For example, patients with brain surgeries who are in coma, in those situations, we can just avoid EEG and use EOG. Now in the future work, we would like to include EMG channel as well. Because in this work we have considered only EEG and EOG, so including EMG will result in an improved accuracy. And also we would like to validate our results on a much larger data set. Here are the references. And I would like to thank you all for patiently listening to this presentation. If you have any questions, please let me know. Thank you so much.